Hello and welcome to our 13th lecture of our course on photonic devices. On today's lecture we are going to discuss the concepts of emission and absorption, focusing in semiconductor devices. So today we're going to discuss the two basic processes with which matter interacts with electromagnetic radiation. And these are the processes of emission and absorption. So emission of electromagnetic waves can happen in the form of light, visible infrared or UV light, terahertz radiation, microwave, and so on. And absorption can also happen in different types of materials. Well, in these processes, the conservation of energy always takes place. So, for example, if a given material emits a certain amount of energy of electromagnetic radiation, such as light, this energy has to be given off somehow by the material. And one process through which this can happen is by the recombination of an electron and a hole, so an electron-hole pair. A process through which the electron loses energy, and this energy, is transformed in the emitted light or the emitted electromagnetic radiation. If you think about absorption, you think of a ray of light impinging on a material. The energy absorbed by the material can be used by the electrons in the material to rise from the valence band into the conduction band, and thus the electrons gain energy which is derived to it by the electromagnetic radiation, i.e. light or other form of radiation. So in absorption, the energy gained by the charge carrier, which can be the electron, is equal to the energy of the absorbed electromagnetic wave. So we're talking about a material in which light is impinging. So we're going to represent light in this way. And if we look at the band diagram, so if this is a semiconductor material, this would be the conduction band, this would be the valence band, and you might have an electron which is down here, and which, through using the energy of the electromagnetic radiation, which has a certain amount of energy, this electron can rise, and therefore it would leave behind a hole here, but it can rise, gain energy, and move into the conduction band. So this is the process of absorption which can happen. So the energy of the photon, or the energy of light or other type of electromagnetic radiation, is given to the electron in order for it to gain energy and rise into the conduction band. Of course, this can happen in discrete levels as well. For example, in gases, in other types of medium other than solids. So you would not have bands, you would have discrete levels, and similar process could occur between discrete levels, okay? But on this course we're going to be mainly focusing on semiconductor devices, in optoelectronic devices. In emission, on the other hand, the energy lost by the charge carrier, and we're talking about the electron here, is equal to the energy of the emitted electromagnetic wave. So you have a material, and again we're going to discuss semiconductors here, but it's going to emit light. So this is the wave, the electromagnetic wave. So again, with the band diagram, conduction band and valence band down here, separated by the forbidden gap, well, what can happen is that if you have an electron which is in an excited state here, right, it can lose energy by recombining with a hole or an empty state down here that the electron can occupy, right? And in this process it would lose energy. and the energy loss could be, among other things, given off as a photon or as a electromagnetic radiation. Okay, electromagnetic wave radiation with a quantized energy, okay, which is a photon. Again, this process can happen in media with discrete energy level, such as gases. You have gas lasers and liquids and so on and so forth. But we're mainly going to be discussing here solid state materials, so optoelectronic devices. That's why we're talking about bands, conduction and valence band, and so on. Well, absorption of light in a semiconductor can happen when an electron in the valence band makes an upward energy transition into the conduction band. So this is what we discussed. The impinging light gives energy to the electron, which can then gain energy and rise from the valence band into the conduction band. For in the process of going from a lower energy state in the valence band to a higher energy level in the conduction band, the electron is gaining energy, right? Which is supplied by the photon or by light. So in absorption, the energy gain is supplied by the absorbed photon. And this is a new concept that we're seeing here. The photon is just a packet of light or electromagnetic radiation in general with discrete energy. Okay, so just electromagnetic radiation, a packet of electromagnetic radiation with a fixed or quantized amount of energy is the description of what is a photon. So it's just electromagnetic radiation such as light or other type of magnetic radiation with a quantized amount of energy. And this energy that this electromagnetic radiation must be enough, right, so that the energy given to the electron is the energy is enough energy that it can rise up to the final energy level right here in the conduction band. So it would have in this case to be larger than the gap energy, right? So the energy of the absorbed photon is the difference between the energy of the final state, so E2 in the conduction band, and that of the initial state, E1 in the valence band. Okay, so the photon energy is equal to delta E, which is E2 minus E1. So this illustrates, you know, with the band structure, the process of absorption. So again, you have an impinging photon of light with a fixed amount of energy. So it's a packet of energy with a fixed amount of energy, a quantized amount of energy. And this energy is given to the electron, which is in the state with energy E1, in order for it to gain energy and rise up to a level in the conduction band, which we're calling E2. So the amount of energy that must be given has to be equal E2 minus E1. Okay, so delta E here has to be equal E2 minus E1, and this is the energy of the photon, which is then annihilated. It no longer exists, right? And the energy is supplied by the electron, which rises up to the conduction band to the level E2. So the photon energy, so the energy of the quantized photon, delta E in this process of absorption, can be related to the frequency of the photon, or the frequency of light, of the electromagnetic radiation, by this expression, right? So you have Planck's constant multiplied by the frequency of the photon is equal to the energy of the quantized photon. So this is the energy, Planck's constant times F. Sometimes physicists like to use the variable ni, right, in place of the frequency F of electromagnetic radiation, but this is the same thing. And well, so this gives us the energy of the packet of light, or the energy of the photon, where h is just Planck's constant, as we said, which is this in eV second, or can be given in joule second as well. And using this, we can calculate the energy of the photon. Well, if this is the frequency of electromagnetic radiation, and we know that the frequency is equal to the speed of light, or the speed related to the electromagnetic radiation divided by the wavelength, right? We can relate frequency and wavelength in this way. And smaller wavelength electromagnetic radiation, such as blue light or UV light, will correspond to higher frequencies, of course, and this will correspond to photons with larger energy, right? So larger energy. So the smaller the lambda, the smaller the wavelength. If you compare UV light with infrared or visible light, or even terahertz, it has the UV light has a smaller wavelength and therefore a higher frequency, and therefore the photons will, in this case, have more energy. So UV light or lower wavelength radiation would make it more probable that because of the higher energy, electromagnetic radiation with lower wavelength could make the process of absorption possible, because the energy would probably be larger than the forbidden gap energy here. Whereas perhaps if you had a longer wavelength electromagnetic radiation, the energy would not be enough for the electron to make the transition into the conduction band. So depending on the wavelength of the electromagnetic radiation, this transition could be possible or not. So the material will absorb certain types of electromagnetic radiation depending on the band gap, but might not absorb other types of electromagnetic radiation. Again, the energy must be enough in order for the electron to make the upward transition. And if the wavelength is too long, such as in infrared light or terahertz and so on, this transition, depending on the band gap, might not be possible, right? So the energy goes up with frequency. So a question that rises is, how do we calculate the number of photons impinging on a material? So let's say that you have a beam of light with a certain power, P, which is impinging on a semiconductor, which absorbs it, through this process we've described, so that the electrons rise up, so that many electrons rise up to the conduction band. How do we know how many photons? If we know the power, which is usually the quantity that we know when we are measuring things on the lab and so on and so forth, if we have access to power, how can we find out the number of photons which are impinging on the material per unit time? Okay, so the number of photons per unit time will be equal to the power. So in the expression here we're calling the power P naught. Okay, so it's P naught divided by the energy of a single photon, and this will depend on the wavelength, right? The wavelength of the photon will determine the frequency of the photon. So we're assuming that we have light with a specific lambda and a specific frequency. Could be UV, visible, infrared, and etc. But if we divide the power of the beam of light by the energy of a single photon, we'll have the number of photons per unit time. And this has to make sense, because the power is just the rate of energy per unit time, right? That's the concept of power. So energy, the rate of energy per unit time, which is delivered by the beam. And if we divide this by the energy of a single photon, by dividing the total energy by the energy of one photon, we can find out the number of photons, and therefore we'll have the number of photons per unit time which are arriving or impinging on the material. Okay, so this has to make logical sense, that if you want to find the number of photons per unit time, you just divide the power by the energy of a single photon, which is Planck's constant multiplied by the frequency of the photon, as we just discussed. Now let's discuss emission. Emission of light in a semiconductor device can happen when an electron in the conduction band makes a downward energy transition into the valence band. So again, looking at the band diagram, where we have the conduction band and the valence band separated by the forbidden gap, if you have an electron up here, some level inside the conduction band, which makes a downward transition and therefore loses energy and occupies the place of a hole in the valence band. So remember that this axis here is energy E, right? So, but if the electron makes this downward transition and recombines or occupies the place of an empty state or a hole down here, the energy lost by the electron is given off as, or might be given off among other processes, but it might be given off as a packet of light, which is a photon, a packet of light with a fixed amount of energy or with a quantized energy. And in this process of going from a higher energy state in the conduction band to a lower energy state, lower energy level in the valence band, the electron loses energy and the energy lost is converted into the emitted photon. Now if we want to calculate the energy of the emitted photon, this energy will be equal to the difference between the energy of the initial state, which is in the conduction band, and the final state, which is in the valence band. So it will be E1 dash minus E2 dash. This will be equal to Planck's constant times the frequency, as we've seen, which is the quantized energy of the photon. So in the picture that we have been looking at of band diagrams with the conduction band and valence band, E1 dash would be a state in the conduction band, right? So it would be a state, an energy right around here. This would be E1 dash, and well, E2 dash, an energy inside the valence band, probably close to the edge, to the band edge. So E2 dash would be this, and the difference in energy would have to be the energy of the emitted photon, the photon that's emitted by the material. Okay, so emission and absorption in semiconductors are closely related to the process of generation and recombination of electron hole pairs. So in the process of absorption, due to the absorption of a photon, there's a generation of an electron hole pair. So, you know, again, if you have the conduction band and the valence band, by absorbing a photon of quantized energy HF, an electron which is down in the valence band will gain energy and rise up to the conduction band, right, leaving behind an empty state where it was originally, so leaving a hole behind. So you see that at the end of the process, an electron and a hole pair were generated. So this is the process of generation. An electron hole pair was generated, so this is the process of generation, right? It does not need to be associated with absorption of light or electromagnetic radiation. The energy can be given in other ways, but if the electron gains energy and goes into the conduction band, an electron and a hole are generated simultaneously. The reverse process is the process of recombination, which can happen with the emission of a photon, right? It does not necessarily need to happen with the emission of a photon, but recombination is when you have, you know, an electron in the conduction band, right, and an empty state here in the valence band, and they recombine. In other words, the electron loses energy and fills the state which is empty in the valence band, therefore annihilating the electron-hole pair, because you no longer have an electron in the conduction band, and since this state is filled now, there's no longer a hole in the valence band. So this is the process of recombination, which can be accompanied by emission of light, but in other situations the difference in energy can be given off as heat, you know, vibrational energy in the atoms of the material or other forms. So the recombination can have emission as a consequence or not, depending on the case. Now, the process we have just described is the process of spontaneous emission, where the emission occurs spontaneously, and this is the main phenomena behind light-emitting diodes. Right, so the emission of electromagnetic radiation happens spontaneously by the recombination of an electron with a hole. A related process of great importance is stimulated emission. So as opposed to spontaneous emission, you have stimulated emission. And in stimulated emission, the recombination of the electron with the hole is stimulated by an external photon. And this recombination generates a different photon than the photon that stimulated the emission. So let's look at this illustration right here. Right, you have an electron initially sitting in state E1' in the conduction band, and a hole initially in state E2' in the valence band, and they're just sitting there. But then when a photon passes by, you know, close to the region where this electron-hole pair is, it can stimulate the recombination. Okay, so it is like this photon provides the start of a process. It's like it flicks the electron in some way, and it makes it so that the electron and the hole recombine, and in the process of recombination the electron loses energy and emits a different photon. So at the end of the process you have two photons, one that was passing by and stimulated the process, and which is the incident photon, and an additional emitted photon. So there are two photons at the end of the process. So this is stimulated emission, where you have emitted, where the material has emitted this additional photon by the stimulus of the incident photon. And both photons that are present at the end of the process, the incident and the emitted photon, are related in several ways, and we'll talk about this at the second part of this lecture.